reference, I was fortunate enough to work and build like a massively distributed parallel systems where the system would process like millions of data points in a second. And in Shoppio, it's a retail tech software. Last year we processed about $50 million US dollars in a year, and it's a system that's been up and running for over a year without any issues. And the backend was designed by just me and one other engineer. So that's kind of the backdrop. I am gonna give my speech today. Should not look like this. What's in there? So the outline of my topic is I'm gonna talk about what is functional programming. I'm not going to go too much into the details of the features and what they are, but I'm going to lay a theoretical foundation of how functional programming works. Then I'm going to talk about the benefits of functional programming, how to think in terms of functional programming, and I'm going to also put some light on why functional programming is making a resurgence. There has been a widespread interest in functional programming in recent years. So that's with that outline, let's start with what is functional programming. Before we get to the coding of any kind, I'd like to present you a simple mathematical model of what a function is. It's all looking very different, sorry. So I'll just go with whatever I have in here. So if you just look at it's a very simple definition of a mathematical function. There's three features of this. It's very simple. The function f returns a value. The return value depends on the single argument, or it doesn't have to be single, on the argument x, right? So value of y does not depend on anything else outside of x. And number three, the function f does not interact with any external system. Everything it needs to calculate y is derived from x and whatever computation it does. If I make you remember only one thing from my talk today, I want you to remember this because this has significant implication with the functional languages. So the entire world is divided into two different kinds of language. One is an imperative language and another one is a declarative. So in imperative language, which is probably most common to all of us, you tell the computer how to do things step by step with instructions. So the procedural languages like C or object-oriented languages like Java and C++, they're all imperative language. The declarative language, on the other hand, you tell the computer what you want. You do not tell how to do it. In this room, we all are more or less familiar with at least one kind of declarative language, the SQL query language. You tell the computer what you want, what kind of results you want, and the database server will transform your request into an execution query path, which is the how part of it, and return you the result. You'll see that functional languages fall under the declarative language group. Before I get to the coding part, I want to touch on one theory of language. Every imperative language is Turing complete. What that means that any calculation that is solvable can be solved using branching, which is our if-else, and looping, which is our while or for loop. If you think about it, this is quite remarkable. Whether you're landing a space shuttle on moon or managing the White House distribution for probably what Chaldal does, or figuring out how to do route planning for food delivery like Shahaj, or any sort of complicated computational geometry problems, they all can be solved with two simple things. That is quite remarkable. Now the functional languages come from, their mathematical foundation is different. It comes from a branch called lambda calculus. I'm not going to get into details of what they are. It has to do with the abstract idea of functions, and basically, if you remember y is equal to fx, that's what is the basic foundation of lambda calculus. One last thing before I move on. It has been proven mathematically that all lambda calculus is, it's been proven that all lambda calculus is equivalent to Turing complete. So why this slide is up here? the implication is anything that you can do on an imperative language, C, C++, Java, Python, you name it, you can do the exact same thing, computationally speaking, with a functional language. So they are functionally equivalent. Okay, so that's kind of the foundation I want to lay before I move on. Functional languages are designed differently. I mean, it's by design different. Instead of using if-else, looping, and blocks of statements, like an imperative language, you use higher order functions, pattern matching, tail recursions, and stuff like that. I believe the speakers coming after me are going to cover this in detail, so I'm not going to talk much about what these things are. But let's talk about why these things exist, why functional language is designed differently, and what's the benefit of using them. Right? I mean, everything exists for a reason. It turns out that all the functional language features exist to achieve only one objective. One thing, very simple, right? Easy to remember. They achieve to reduce, eliminate, or isolate side effects. So this is like, if you, I never heard of side effects, why is this important? This is something, an important topic to explore. So side effects really means anytime you're modifying a variable outside of a local environment, for example, you're accessing or changing the value of a global variable, or modifying a static variable, or changing the value of a parameter, function parameter, which is an argument, inside the function, you are generating side effects. Simple concept, but it has a very strong ramifications. So functional languages exist to avoid these side effects. So let's take, I want to just to throw out one example. They're toy programs, right? Just to illustrate the idea of what I'm talking about. So if you look at the function on the left, the function increases a number by 1. On the left-hand side, with the side effect version of the function, it accesses a global value and it increases the value of 1. So how do you write the same function without side effect? You basically pass it as a parameter and add 1 to it. So the first one violates the y equal to fx principle, the tree principle that I talked about. So let's look at the right-hand side one. Basically, it accepts a list as an argument and appends one item to it. This one is also violating y equal to fx principle. Why? Because it is modifying an external, it's modifying an argument that has been passed by reference. So how do you write this without side effect? You just create a new list and return it, and you don't change the original argument. So these are toy programs, but it illustrates a point that any function that has side effects can be rewritten in a non-side effect kind of way. So that's kind of the point I'm trying to get out. So what are the benefits? Why bother with all the side effect stuff, and why bother with functional languages that does not have side effects? So that's the important part. Turns out, if you can write a program that has no side effect, you get some magical benefits by default. Number one, unit testing is a breeze. And why is that? Every function just accepts a parameter and returns a value. All you have to do is assert the return value with your expected value, and you know whether the function is right or wrong. I know you cannot easily do that in all of imperative languages, because you might have to set up an object structure, a class hierarchy, the interactions might be complicated, stuff like that. But for a function, it's easy. Debugging is also easy, because if you ran into a program is behaving incorrectly, all you have to do is just go through function by function, pass the parameters, check the return values. The biggest bang for the buck comes in the concurrency field of it. It may not be obvious, but if you write a program in a functional way, you get concurrency, thread safety by default. You do not even have to do anything. And the reasoning is actually quite easy to understand. Everything is a passing a value to a function, and that stays in the stack of the function that cannot be accessed by any other function parallelly accessing the value, right? So concurrency is by default is given. You don't have to do anything extra. No locking, no shared resource or anything. I'm actually, for the interest of time, I'm gonna skip the hardcore deployment and correctness. This one really means you can modify a running program without shutting it down or rebooting. You can think of where they might be important. Let's say air traffic control system, right? And let's say the missile defense system, right? You don't want to shut down a systems like this. So these are important. Now, the functional languages are by design, they are less complex. So why one should be interested about that? A less complex language means you're spending less time debugging and fixing problems, and you're spending more time building features, right? And it's good as a developer, good for the company. You want to build features and not just spend time trying to fix problems. One point I would have, so before, these are like one of the common ones. Some of them are pure functional language. That means you have to do everything properly, like in a pure functional way. Haskell is one of them. Some languages allows you to do imperative style programming, even though it's a functional language. This is one of those. But the one thing I want to pay focus to is that if you remember the three properties of y equal to fx, right, and the side effects, there's nothing inherent about functional programming to do functional style. Right? You can do functional style of programming in any language, but you have to think a little differently. Right, so I'm going to illustrate that with a quick example. So anytime you need to use locks or modify a static global variable or modify a functional parameter, you can stop and think, what can I do differently to avoid this side effect? And it will result in a better program that is less buggy. And there are some other things. You can replace branching with pattern matching or replace the loops with a map reduce, but these are some features, functional language features that I'm sure you can look up. So I want to go through just a simple toy example, just to illustrate the point that any program written in imperative style can be transformed into a functional style. So this is just a program that runs a race of 3 cars. At every time stop, the cars either move forward or stays in the current position. After 5 stops, the car that moves the farthest wins. So this is what it's just a toy program, right? So let's an implementation of this program. This is the full program, right? That's what it does. It's an imperative style. It uses for and if else branching, accesses some static or global variable. You can turn this program in a functional style and it will look like this. So it's the exact same program written in the same language, but the ideology is different. This one follows all those 3 principles of y equal to fx. Okay, I just want to talk a little bit about WhatsApp. This is one example, one app we're probably all familiar with. There are many production systems running in functional language in the world, many, but this is a very common one. So WhatsApp, this is 2004 data. It processed at that time 70 million messages per second with a 1 terabyte of RAM, and it onboarded 1 million new customers a day. I mean, this is remarkable. And they did all this with 35 engineers. The entire system was running with 35 engineers. The backend was built with Arlon, one functional language, and the founder of WhatsApp actually attributed to the scalability and their the stability of their platform to the language they chose to build it. And the result, if you don't know the story, WhatsApp with 35 engineers got sold to Facebook. Was it Facebook for $19 billion? So in the recent history, in last 5 to 10 years, there has been a resurgence, an interest in functional language. And I would like to touch on that why, and it might be relevant to the people in the audience here. The reason is the proliferation of multi-core systems. If you look at this chart, look at the green line. This is basically the number of, so the green one shows the clock speed of a CPU, and it's kind of stopped growing after 2010 because of the natural physical limitations. So how do the hardware designers, the CPU builders, they provide more speed? By adding more cores. That's why the black line, the number of cores is increasing after that. But how do you take advantage of multi-core, right? The only way to do it is if your program is concurrent. It takes advantage of parallelism, right? If only in that case you can take advantage of multi-cores. So that explains why functional programming is becoming popular. To take advantage of multi-core, you have to do parallel programming. And to do parallel programming, the best way to do it without any side effects, without any race conditions, without any thread safety issues, is to use functional programming. So that's kind of all I wanted to cover. I just wanted to touch base on the basics and some theories. I want to throw out some recommendations, some resources for if any of you are interested. I only scratched the surface of functional programming. There's many more interesting things to learn and to try out. There's some concepts here that you want to look at. Maybe you want to learn a new functional language. There's some resource. I mean, you can find the resource online. I just covered a few over here. And so what are the takeaways? Just to finish up, wrap up my talk here. Y equal to fx with these three properties, the foundation of functional programming. Side effects are bad, and you should try to avoid them. Functional programming is a natural fit for parallel programming because you don't have to do anything extra, comes built in. Thinking functional, even if you're using C or Python or Ruby on Rails, is a skill that will make you a better programmer, and it will help you build systems that's less buggy. All right, I'd like to thank everyone. My Twitter and LinkedIn is here if anyone wants to connect. And thank you everyone for coming to the audience.
My question is, if functional programming is so good, are there any cons to it?
Yeah, I mean it's good in a way. Is Ruby better than Python? Is that kind of question, right? Is C++ better than Java? In some ways it is, in some ways not. It has its places, right? So functional programming is a little difficult to think about, right? If you need some practice. So that's why the functional programming is not common, right? It's not mainstream, not the most popular languages. What would be the cons? Tell us something you can think of.
I think so far from what we have noticed.
Can you think of any tasks that is
So for example, if you're going to be writing drivers which work very closely with the kernel, if you're going to be writing operating system calls, you may want to have very precise control over memory management and the number of instructions your code is compiling to. In such cases, imperative languages are a natural fit because you not only care about the functional patterns, but you also care about where the byte is being stored in your memory. So some places it actually is a very natural fit. But I think for the overwhelming majority of our use cases, I'm talking about us boring enterprise software developers, functional programming actually fits really well. So for most of us, I think we just don't use it, but I think it can definitely be used.
Okay. My second question is, are there any performance implications?
Yeah, so you'll see, if you remember the example, some of the times it creates new lists so that it does not violate. That's one thing, and there's other implications. There's a feature called continuation, which means you operate on a function and you pass in the result to a third function, and you might want to call you recreate stack. Recursion is one big tool of functional paradigm, and the recursion you can run out of memory stack is possible. But there are the compilers are becoming smart depending on what language you're using. So they have techniques to eradicate this issue. But memory overrunning memory capacity is a possible side effect of using a functional language.
Okay, last question. Should I always try to write code that is functional?
Well, in ideal world, right? But of course, in a non-ideal world, there are bosses and there are deadlines, and there are people asking you why this thing is not done yet, right? So, joking aside, in a way, it's a good habit to build up, right? It's not going to happen overnight, but let's say you start thinking in functional ways, and you cannot completely remove all side effects. It's not possible because an application has input and output. And if you think about it, input and output is actually side effects. But what you can do, you can isolate the side effects, right? Instead of sprinkling the side effect behavior all over the system and making it very difficult to trace what's happening with the object relational models and the class hierarchies and all of that, you can do functional programming as best as you can, right? And then like isolate, separate out the issues that cannot be possible to make functional or will take a lot of time.
Thank you.
Should I answer more questions or we're done? Yeah. This one last. Okay. I think it's the last question. I've been shown a death threat, so this is the last question I can answer.
So how does functional programming handle concurrency and parallelism?
Oh, right. So if you, I think that I would like to ask the question: why does thread safety occurs? Like why the issue of the resource sharing comes? In parallel programming, if you access a shared resource, then you're running into issues of concurrency. Who gets there first? Who's modifying all that stuff, right? But in functional programming, there is no shared resource. So this is the thing to be excited about. If there's no shared resource, every operation comes as an argument or parameter to a function, right? That's all you're doing. And what happens? The parameter goes to the local stack of that function, and no other part of the program can access that, right? So you have this. Let's say you have this 5 functions. If let's just do this 2 functions. If this one does not rely on this function to operate, you can run them in parallel because there's no dependency between each other. So compilers, the functional language compilers, are actually do this. You write a program without worrying about concurrency or parallelism. It will run things in parallel based on the number of cores available on the machine because it can identify what are the dependencies. It's very easy to do. I hope this answers the question. I'm happy to talk more after this. All right. Thank you, everyone.